Question number 7. Y equals negative 4x, y equals negative x cubed. And it says, why can't, when you find the area between these two curves, why can't you write it as one integral? Why does that be written as two integrals? We're going to answer that question by graphing it. So, if I look at the line negative 4x, the y-intercept, it goes down 4 into the right one, and you have your line. If I look at negative x cubed, it's also 0, 0. But this curves up to the right, and it curves down to the left, just like that. Because it's negative, it gets reflected. I want you to notice that this area, the line is on top. And in this area, the curve is on top. So because they switch positions, you can only write it as one integral if the whole time the top is the top and the bottom is the bottom. But what happens if the top and the bottom, they switch places? Well, then you need two integrals for that. So when the line is on top, that's an integral. And then when the curve is on top, that's a second integral, and you'd have to write it as two integrals. So what would be a good sentence here? So between negative 2 and positive 2, so between negative 2 and positive 2, that's what we have here. Neither function is greater than the other function for the whole interval. So for this one, the line is greater, and for this one, the cube function is greater. Because they switch which one is greater, you would have to write it not. Now, it says then use symmetry of the graphs to write it as one integral. So if I did that, I could go from 0 to 2. So when I plug in 2, it's negative 8, negative 8. So 2 is a point of intersection and 0 is. So I can go 0 to 2. I can double that answer. So I can find this area and double it because of symmetry. And then what's on top is negative 4x subtract, no, what's on top is the curve. That's negative x cubed subtract negative 4x. Do I have to find the area? Then use this to write it as a single. So I don't need to find the area. Just this concept that you can't write it as one integral from negative 2 to positive 2, but you could write it as one integral for this area and then double the answer because of the symmetry of the graph. Number 8. Without using a calculator, sketch a graph showing one of the regions bounded between y equals cosine x and y equals 2 minus cosine x. So I need to know the graph. Cosine x for the graph starts on top. See if I get this graph. All right, so there's the graph for cosine x. It starts on top, it goes to the bottom, goes back. That's one cycle. Now 2 and negative cosine x. So negative cosine x means that this would be reflected, but then it would shift up 2. So if it shifted up 2, it would go 1, 2. It would share this point. And then it would have this kind of look to it. So instead of this, it does the reflection and does the same thing. So you can see it goes from 0 to 2 pi. And what's on top is 2 minus cosine x. And then what's on the bottom is just cosine x. Now, how would I find this area? Combine like terms. Now, I can integrate this separately. So the integration of 2 is 2x. The integration of negative 2 cosine x would be negative 2 sine x. And we're integrating from 0 to 2 pi. Then you plug in the upper limit. Oops, that's 2 pi. Plug in the lower limit, that's 0. The value of sine at 0 is 0. So this is 0, this is 0. And so you're left with 4 pi. The value of sine at 2 pi is just like 0, it's 0. So the answer is just 4 pi. Number 9. Use a calculator. That's good. To find the shaded area between the curves, f at x equals 2 sine x, and g at x equals negative 3 cosine x, from 0 to pi. Show an integral setup. So we need to use our calculator, see which one is on top, which one's on the bottom. Because cosine is negative, that one's going to be on the bottom, right? And sine's going to be on top? Yeah. So I'll show you the calc, but sine is the one on top. So if you think of it, sine starts in the middle, negative cosine will start below it. And so this curve compared to this curve is going to be on top. Okay. So how would I do that? Let's look at here at the graph. Oops. Erase this. And so the first function I'm going to type in is 2 sine x. Here, let me undo all that. And let me start again. So 2 sine x now I'm going to change the window and so I know I'm going from 0 to pi, right? That's what I said. And then the y minimum is going to be negative 3 from cosine up to positive 3. Alright, so that's y equals 2 sine x. I'm going to press tab again. I'm going to put in the second function, which is negative 3 cosine x. Oops, why did I put in sine? So negative 3 cosine x. I want you to notice that there are 2 integrals, so that the blue is on top and the red's on the bottom, and then it switches. So I need to find where this point of intersection is, right there. So let's do that right now. To find that point of intersection, press Menu, Analyze, and we're going to point of intersection. That's number 4. It'll ask what's the lower bound, so that means just go to the left of where the point of intersection is, press Enter. And then it'll say where the upper bound is. We're going to shade over it. And notice as I do that, the point of intersection pops up. Isn't that beautiful? And all I need is the x coordinate, which is 2.159. So this is actually going to go from 0 to 2.159. And then after that, it switches. So I'm going to set up a second integral. that goes 2.159 to pi so that I can complete it. And now negative 3 cosine x is there, and then subtract 2 sine x. And now that's what I'm going to type in. With this calculator, you can integrate what number is that? Number 7. It'll give you, it says what graph? And then the lower bound goes 0. Oh, it's not finding it. I did the wrong one. So let me escape from that. There is a different one that says the area between. Bounded area, number 8. That's what I made a mistake with. So the lower bound is 0. And the upper bound is pi. And then the answer that you see there, 7.211, that's the answer. So this one right here, that answer above. So the calculator, we need to know how to set it up to write it down properly. But the calculator did all of it and did the work for you. So that's why I like using the calculator. So it's 7.211. Right there. That's the area. It's good to practice, right? To try again, you could rewind like it's a tape. You could go back to the beginning and try again and see if you can use your calculator to find bounded area. All right, number 10. The graph of a function that you see there is on the right. It says evaluate from 1 to 7. So when I integrate, I'm going to find the area. So from 1 to 7, how would you find the area? Can you see the different shapes that you would find the area of? And then figure that out. So let's say I break it into 3 shapes. A trapezoid, a triangle, and a rectangle. Can you press pause and try to find the area of each one, and then I'll do it too. So for a trapezoid, it's 1/2. So again, I'm integrating from 1 to 7. So it's 1/2. The width is 1. The first height is 3 plus the second height, which is 1. So that's the trapezoid. The triangle, half. The base of it is 2. And the height is 1. And then one more, the rectangle, so length times width, so 2 to 7. So it's 5 times 1 is the height. If I needed to, 3 plus 1 is 4, and half of 4 is 2. Half of 2 is 1. Oops, there's a 1 in there. And then if I add it up, I get the answer 8. 10b, determine the average value from 1 to 7. So average value, you integrate, wait, I just did that, and then divide by the difference of the bounds. So that would be 8 divided by 6. Don't reduce it down. C, determine the answers to parts A and B if the graph is shifted upwards 2 units. So if it's been shifted up 2 units, what would that change? And so if it gets shifted up 2 units, how much area does that add to what I already have? And so it creates a rectangle. That would be 7. No, 1 to 7 is 6. So 6 by 2. So it'd add an area of 12. So you would add 12 to 8. And your answer would be 20. And then the average value would then be 20 divided by 6. And then don't reduce that down. All right, turn the page. Number 11. In number 11, you're integrating from 0 to 8, x cubed dx. And it says, first, sketch graphs and approximate the values, and we're using a Riemann, and a trapezoidal rule. So if I sketch the graph here, I mean 8 cubed, it's a big number. I don't want to go 8 times 8 times 8, but I'm not going to worry about the graph. So I'm just going to worry about the setup of it. So I have a sense of what it looks like, and I have a sense of the bounds here. So it goes from 0 to 8. So the first it says n equals 4. So the setup of that would be, first find the width. So it would be the top subtract the bottom divided by 4. So the width of each rectangle would be 2. The first interval will go 0 to 2, so midpoint would be 1. So you plug 1 in. I'm not going to reduce it down. The next would be 2 to 4, so you plug 3 in. And I think you can see the pattern here of what it would look like. So that would be a midpoint Riemann sum. B, using the same thing, a trapezoidal with 3. So the width, again, the top subtract the bottom divided by, oh, this time it's 12. Oh, totally. Oh, same one, sorry. So 11, you have to do both the rectangles and the trapezoid. So the width is the same. And so for a trapezoidal rule, it's 1/2 times the width, and then each height within intervals. So the first one I would plug in is 0, and then you would double, and the next one would be 2, and then the next one you double would be 4, and the next one you would double would be 6, and then the last one you would not double. And that's what it would look like. So that's the trapezoidal rule. These are the heights, and the first height and the last height is not doubled. All right, 11b or 12. In number 12, we're integrating from 0 to 12, negative root x dx, n equals 3. And again, if I had a picture of this graph, negative root x would look like this as it would come down. And we're going to use rectangles or trapezoids to do it. So in part A, if I'm using a midpoint Riemann sum from 0 to 12, the width would be 12 take away 0 divided by 3. So we'd start with 4. A midpoint, the interval is 4. So from 0 to 4, the middle value is 2. So I would plug 2 in for the height. And then from 4 to 8, the middle value would be 6. And then from 8 to 12, the middle value would be 10. And again, you're plugging these into the function. And that's called a midpoint Riemann sum. For a trapezoidal sum, it's 1/2 times the width. The first height, you'd plug in 0. Then you would double the next height. You would plug in 4. Don't even reduce it down. The next one you would plug in 8. The next one you would plug in 12. And then the last one you'd plug in, that would be it, right? So there's 3 of them. So the last one wouldn't be doubled. So you would use 0, 4, 8, and then the last one would not be doubled. There it is. Number 13. A pasture is bounded by a river and 2 fences, as shown in the picture here. Approximate the total area of the pasture using a midpoint Riemann sum, using 5 equal subdivisions, and then the trapezoidal rule and so on. So for part A, step 1 is to find the width. So for this one, it bounds, it goes from 500, 0 to 500. So 500 take away 0 is 500. And then divided by 5. That would mean each interval is 100. So we would start with 100. Now a midpoint. So from the first interval goes 0 to 100, so the middle is 50, so you'd use 210 for the height. Next one, you'd use 150 for the height. Then you'd use 250 for the height, 350 for the height, 450 for the height, and then you'd have it. And that would be in yards squared. Have no desire to simplify that. B, for a trapezoidal rule, again, the upper minus the lower bound, but this time divided by 10. So now it's every 50. So now the area would start with 1/2 times 50. So the first height is 250. Then every 50. You double. You double. There's going to be a lot of numbers here. You double. You double. I'm going to say it again. You double. You double. You double. You double. And then when do you start doubling is at 0. And again, that would be at yards squared. The trapezoidal rule, and this is a midpoint Riemann sum. 14. Two men in a search party begin walking from search hardcores at the same time. One walks north at a rate of 4 feet per second. The other one walks west this way at a rate of 3 feet per second. After both men have walked for a minute, find the distance separating them. So here the distance separated. If you're walking 4 feet per second, then there are 60 seconds in a minute. So 60 times 4, that's 240. That's how many feet. And then 3 times 60, that's 180. That's where that number comes from. Using the rate times 60 seconds, that gives you the distance. And so I'm going to call this z. So it'd be z squared is equal to 240 squared plus 180 squared. So if you solve that, z is equal to 300. The question asks, that's part A. Part B is the rate at which the distance between the two men is changing. So dz by dt. So I have z squared is equal to x squared plus y squared. That's the Pythagorean theorem. Then I'm going to take the derivative with respect to time. So 2z dz by dt, 2x dx by dt, 2y dy by dt. Then plug in the values that you know. So you know z is 300. That's what I'm looking for. X is 240. And the rate is 4. Y is 180. And the rate is 3. And then all you have to do is solve that. I don't mind if you use your calculator. So put that in your calculator, and the answer would be 5 feet per second. You could also notice it's a 3, 4, 5 right triangle with rates too. Number 15. In number 15, you have a graph of a derivative. I'm going to draw a derivative line. So when I look off a graph of the derivative, look for the x-intercepts. -3, 0, and 3. Then look for above or below. So it's below and then above, below and then above. So that means there's a minimum here, a maximum here, and a minimum here. If I do the second derivative, I'm looking for turning points. So there's a turning point at -2 and a turning point at 2. And it increases, decreases, increases. So these are points of inflection. If I want to graph the second derivative, then at -2 and at +2 for the second derivative, those are intercepts. That's where the derivative is equal to 0. And then it's increasing, decreasing, increasing. Now, the point of inflection for the first derivative is the turning point for the second derivative. So at 0, there's a turning point. So when I think above, below kind of thing, so it's above, below, above, here it is. At 0 is that turning point because it's the point of inflection for the first derivative. For B, it says graph the function so I'm going to use -3, I'm going to use 0, I'm going to use +3, and I'm going to use -2 and +2. And it says it passes through the origin. So I know, I'm going to look here, it decreases and then increases. So this is a maximum. So when I think of it, all right, so it decreases and then it increases. Now, it's concave up and then it's concave down. And then it's concave up. And so this shows the minimums and the maximums and concavity that match this number line. So does it decrease and then increase? Does it increase and so on and so on? Do these match? And does the concavity match? Does it concave up and then concave down and then concave up? And the only point we know on the graph is 0, 0. Otherwise, we're just looking for increasing, decreasing, and concavity. Number 16. Use the trapezoidal rule with 4 equal subdivisions. So I want to find the width. That's 8 divided by 4. So that's the trapezoidal rule. And then I'm going to plug in 3. And then I'm going to double. Now the width is 2, so the next interval will be at 5. We're counting by 2's. Next one would be 7. Then it'd be 9. And then the last one is 11, but I don't double it. And that's what it would look like. Alright, let me do a few more here, and then I'll have to do another video before the bell rings. So this is the fundamental theorem of calculus, the second part, because I see derivative and integration. So it's a substitution problem, and then if there's a hook. So the hook is 2 from the bound, and that's it. Number 18, same thing, fundamental rule of calculus. Make sure you know the order here. So if I plug in 5 and do the derivative, we start with 0, subtract, then plug in x squared, and then the hook. Number 19. The derivative then, again, I plug in the upper bound and then the hook, subtract the lower bound. There is no hook there. The derivative of just t is 1, and that's it. For number 20, find the value of this definite integral. So So we're going to integrate from 0 to pi over 4. We've got to know our integration rules. The antiderivative of tangent is secant squared. Right? The derivative of tangent is secant squared. No, there's nothing for tangent. I'm just going to use my calculator. So do you know how to use your calculator to do this? Calculus, integrate. I'm going to integrate from 0 to pi over 4. I'm just saying we don't have an antiderivative rule yet for that. So it's 0.346. You don't have to round. You can truncate. All right, that's going to be it for now. Mr. G Math over and out. Until next time, I'm proud of you for doing your homework. And then we'll do one more video to finish off the assignment. Until next time.